All right, welcome back. Last time we talked about arguments right, and their parts, and we said there's two broad classes of arguments. There's deductive and inductive arguments. Now, this being a logic class, the bulk of it is going to focus on deductive arguments. Before we start getting into the details of that, I did want to spend a little more time on induction because it is so important in our everyday lives. Right? An argument consists of premises, a conclusion, and an inferential relationship between the premises and the conclusion. And that's the part that's not always on the page if you see an argument, but it's always there. So we saw that in a deductive argument, we can call the inferential relationship either valid or invalid. And we defined valid as, if the premises are true, the conclusion has to be true. Or for the premises to be true and the conclusion false at the same time, then it's invalid. Um, not all arguments are deductive arguments. So again, deductive arguments, when they're good, guarantee a true conclusion, right? And good means valid plus true premises. We call that sound. So a sound deductive argument has a guaranteed true conclusion. Can't possibly be false, right? Um, but we don't always have those kind of arguments available, right? And as we know, a lot of things in this world are not guaranteed the way the conclusion of a good deductive argument is. For example, um, every morning I get in my car and I drive to work. Do I know for sure, right, that I won't get in an accident? Well, no, right? I mean, if I knew for sure that I would get in an accident, I certainly would call in sick, right? Um, but what we do often do with lots of things in our lives is, yeah, we take on a little bit of risk, but we use a good inductive argument to say, well, it's probably the case that I won't get, you know, to a greater or lesser degree. And if the probability is high enough, then I think, well, I'm going to get in the car. You got to take a little risk here and there. I'm going to cover three general types of inductive arguments, and then I'm going to talk a little bit about how induction is thought of in sort of the philosophy of science. So the first type of inductive argument I'm going to talk about we call next case induction. So all inductive arguments just take some discrete observations as premises and then draw a conclusion from those, right? So one way that might happen, I might notice that, several days in a row, the mail carrier arrives around 11 a.m., right? How many times do I observe that? I don't know. Say I observe it for a week straight. Uh, on that basis, I might draw a conclusion. One type of conclusion I could draw, right? So I've watched the mail carrier show up at 11 a.m. for a week straight, and now it's Monday at 9 a.m., right? I could say, hey, the next time the mail carrier comes, it's going to be around 11 a.m., right? This is next case induction. We're observing some number of cases with some property, right? And we conclude that the next observation will have the same property, right? So another argument of this sort, I might observe 100 crows, right, the bird, and observe that they're all black, right? And I might draw the conclusion after seeing 100 black crows that the next crow I observe will be black. Right? So this is next case induction. Here's the general form of next case induction, right? So these F's and G's are just basically just mean like F1 is like crow one, right, that I observe, and I notice it's G, it's black, right? Or I might notice the mail carrier arriving, right? So F might be a thing, it might be an event, but mail carrier arriving time the first time, 11 a.m., right? Mail carrier arriving the second time, 11 a.m., right? Crow true, black, right? And on, right? So I'll observe repeated instances of some object or event having some property up until n times, right? So maybe I observe it 7 times, maybe I observe it 100 times, right? And that, n might be 7, n might be 100, right? But wherever my observations stop, that's n. And then the next, uh, right, the conclusion I draw, right, we'll call it, number n plus 1, that next one will be, that next f will be, right? So again, if it's 1 through n is like 7 observations of crows being black, then I conclude the 8th crow I observe will be black. So that's next case induction. And, what makes it why we call it next case is the conclusion we're drawing, right? We're drawing a conclusion about the next observation, similar to all the previous ones. You've probably all, foods you don't like, if you don't care for onions, right? I imagine you tried onions some number of times, and maybe after, onion number 4, you said, you know what? The next onion is probably going to be gross to me too, right? And so I'm just going to stop eating onions, right? We do this all the time, right? Subconsciously, maybe sometimes, geez, I've dated 4 Pisces. They've all been jerks. But the next Pisces I date will be a jerk too, right? Whatever, uh, again, pretty common thinking. Now we can make it formal. So again, inductive arguments are not valid. They don't have that kind of inferential relationship. That kind of inferential relationship only applies to deductive arguments. But they do have their own kind of inferential relationship between the premise and the conclusion. So the more probable the premises make the conclusion, we call that argument stronger, right? Um, if the premises do not make the conclusion very probable, then the argument is weak, right? So the name for the kind of inferential relationship you have in an inductive argument is either strong or weak. And unlike validity and invalidity, strength and weakness can be a matter of degree, right? An argument might be more or less weak, right? So, you might ask, well, how many crows do I need to observe to have a strong argument, right? Reasonably, the next crow I observe will be black. Is 2 enough, right? Is 10 crows enough? Is 100 crows enough? Well, to really answer that question properly, you need a little statistics, right? I don't think we'll have time to cover that in this course. If you take my critical thinking course, we do cover some statistics. So for now, we'll just keep it at an intuitive level and say, well, yeah, 2 observations is not the strongest inductive argument. 100 observations seems pretty strong, and it depends on the context too, really. I mean, how many times do you need to try onions before you decide you don't like them? Usually after a couple times, 3, maybe 5, we'll give up on a kind of food and decide it's not for us, right? So I can't give you an exact answer without some statistics on how many crows you need to observe, but you know, it's a matter of degree and strong to weak for that kind of relationship. If we have a strong inferential relationship and the premises are true, we call that cogent, right? Remember, just like with deductive arguments, if we had a valid argument and the premises were true, we called it sound. Well, with inductive, strong argument plus true premises equals cogent. Well, in that way. And a cogent inductive argument gives us a conclusion that is probably true. And probably true is good enough to get through life, right? If I invest in something and I know I'm probably going to make money, well, I'll keep doing it, right? If I win 51% of the time, I'm moving to Vegas, right? Because that's really all I need over the long run is probably pretty well that way. So again, as I mentioned in the last slide, what makes an argument strong? For the purposes of this slideshow, it's going to have to stay a little, kind of intuitively, right? I don't. This slide says, yeah, this slide is from I think a different class where we do cover statistical methods. If we have time, I may talk about it, but I don't expect we will in a logic. A lot more time on deduction, right? But yeah, 1 or 2 observations, typically kind of weak, and if you've got dozens of observations, that's pretty strong. That's that for now, right? Okay, so we've seen next case induction. There's another sort of conclusion we can draw from similar series of observations, right? So suppose I have the exact same premises. I observe the mail carrier arriving at 11 a.m., say 10 times in a row, right? Instead of concluding that the next time the mail carrier will arrive at 11, I could also conclude the mail carrier always arrives at 11, right? I can draw a general conclusion, general induction, right? After observing a bunch of black crows, right? 100 black crows, I might conclude all crows are black. All onions are gross to me, right? So uh, instead of drawing a conclusion about the next case, about a specific case, we're drawing a conclusion about all GFs, right? Um, Now, you may notice that this general conclusion entails the next case conclusion, right? if all crows are black, then certainly the next crow I see will also be black. So this is a much stronger conclusion, a much sort of riskier conclusion to draw. But we do it, right? We do it in science all the time. Um, and it's really hard to draw those, to do general induction well, right? That's why of science, if you studied it, it's a whole history of, failed and revised theories, because we think we have a general answer and it turns out it's wrong and we have to come up with a new theory, right? Um, but it also is, pretty impressive. We've made progress, right? And we have figured out some basic laws that seem to hold all the time, and they've even allowed us to sort of go to the moon, and we get onto airplanes with regularity, and are not too worried about, um, you may be worried about some mechanical thing failing, right? Which will be the fault of, some mechanic, but we're not worried about the laws of nature suddenly being wrong, right? And the laws of aerodynamics and the plane just dropping out of the sky. We feel pretty confident, even though it's only based on induction. So here's the general form of general induction. Again, the same premise, the premises are the same as next case induction. So premise one, F1 is G, crow one is black, onion one is gross to me, however you want it, right? F2 is G, F3 is G down to Fn, however many observations you make. But here the conclusion is all Fs are G. All crows are black, all onions are gross. Okay, here's the third type of induction. So as far as, homework and quizzes and stuff, um, you know, I do want you to remember these three kinds of induction and be able to recognize them. We've covered case in general. Here's the third kind that you need to learn. Sometimes it's called abduction, sometimes it's called IBE, or inference to the best explanation. So while next case induction and general induction were very similar in structure, IBE is pretty different, right? So um, the conclusion could be general or it could be something very specific. Um, you can think of IBE as kind of like a detective novel, right? We start with various observations, certain facts, right? Those are our premises. Um, then, as one of the premises, we come up with a hypothesis that explains all those observations. And if it turns out that that hypothesis is the best explanation, then we conclude that it's true, right? So here's an example. Fingerprints were found at the scene of the murder. Nate was observed leaving the scene right after the murder occurred. Nate was overheard making threats to the victim. The best explanation of these facts is that Nate committed the murder, therefore Nate committed the murder. So here's the general form of abduction, or IBE, right? So we've got some observation or some fact, right? We've got however many observations or facts, overheard, uh, arguing with the victim, and so on. Once we've listed all the facts, the next premise is, so here we're at n plus 1. The best explanation of fact 1 through n, is P, some hypothesis. And then conclude, therefore, P, that hypothesis is true, since this is the best explanation of all these facts. You might ask, well, what makes an explanation the best one, right? Um, well, we have some criteria for that, for deciding what makes an explanation a good one. First of all, to be the best, it just has to be better than the other ones, right? Um, well, what makes one better than another? Well, first of all, an explanation should entail or explain all of the observations, right? It should predict. Um, for example, if one of the observations we made is that Nate is teaching class at the time of the murder, um, well, Nate being the murderer doesn't predict that Nate would be at a totally different location at the time of the murder, right? That doesn't explain that fact at all, right? Um, so if our hypothesis can't explain all the facts, including that I wasn't there at the murder or I was somewhere else, then that's gonna be a problem for explanation, right? Um, but suppose we have more than one explanation that does explain all the facts, right? Forget about me being in class, and let's just suppose the facts were, yeah, Nate was covered in blood, right? Nate was heard making threats, and I didn't have an alibi. Um, I maybe, right? Here's probably what I would do at in my trial, right? I would come up with another explanation. I would say, actually, the police took my clothes and they soaked them in blood, right? And I was framed, and um, it wasn't me shouting the threats, right? They recorded my voice and did AI and did it, right? So I could come up with another explanation that explains all the facts. It was, the have to frame me, right? So which one is better, right? Nate is the murderer, or Nate was framed by the cops? Well, when we have two explanations that explain all the facts equally well, then we'll tend to go for the simplest one. Now, that might seem strange. Why should the simplest one uh, be the right one? Well, I'll tell you a story in a minute about, we do just sort of assume that, and you may argue that we don't have any basis for that assumption, right? Why does the universe need to be simple? Why does the truth need to be simple? But it does tend to guide us to the truth, it seems. Um, we also like explanations that make novel predictions true, right? Again, so if Nate is the murderer, you might say, I predict that we might find more evidence at his house if we search his house. And if you go to my house and you find, whatever, more, some of the victim's blood at my house, right? Then that's for that explanation. So we like simplicity and we like predictive power. What makes for for a better explanation. So many people have argued that scientific inquiry is a form of IBE, right? We come up with a scientific hypothesis that's supposed to explain all the phenomena we observe, and we determine whether it's the best explanation by uh, making sure that it has simplicity and predictive power, right? Um, and we compare various theories, right, various hypotheses, and see which one predicts the most facts, and then which one is the simplest. Now, there have been situations in history where we had two theories and they both predicted the facts. And we ended up having to go for simplicity to choose one over the other. So, for example, um, before we decided that the sun was at the center of the solar system, we thought that the Earth was, right? Because it seemed to match the facts, right? You walk around on the Earth and you seem to see the stars go across the sky, and so it seemed to make sense that everything went around the Earth. And we thought they went around in perfect circles because there's simplicity in the perfect circle, right? Um, but then what happened was, if you if you carefully observe the night sky, which people have been doing for thousands and thousands of years, they notice that not all the heavenly bodies go in, uh, smooth, straight arcs across the sky. If you observe them night after night, they might start to actually just go backwards for a while. Oh, Mercury's in retrograde. People that like astrology. Yeah, I'm all messed up this week. Mercury's in retrograde. That just means that Mercury is advancing across the sky and then stopped, right? Right. Um, so that was hard to explain on the Ptolemaic theory. What they did is they added little orbits within orbits, which them in the photo there, right? So they sacrificed some simplicity, right? But in order to predict all of the data, predict all the observations. Um, but it got more and more complicated the better they got at observing, with better telescopes and stuff, at observing things. They had to have epicycles within epicycles and stuff like that. And Copernicus came up with the idea, along with like Kepler, that um, what if we put the Earth at the center of the solar system, have the planets going around in elliptical orbits? They're not as perfect as circles, right? But we can get rid of all the epicycles. Um, so there was a lot of, argument over which one was which for a long time. Ultimately, we settled on the Copernican theory because it was the simpler one, and turned out it was right. And it made a very bold prediction. It took hundreds of years for us to be able to test it, right? But if you send a satellite out towards the edge of the solar system, it's not going to pass the sun or Mercury or Venus, right? It's going to go out, so it'll Mars and so on, right? Um, so simplicity in this case was a guide to the truth, right? And this has tended to be the case throughout the history of science. So even though it might seem there's no rational basis for it, simplicity is our guide in when it comes to IBE. So while I'm going to spend a few slides just talking while I'm kind of into a little philosophy of science here. The problem of induction, right? So again, we use induction all the time. Um, you decide what you want to eat, right? You decided to use it to decide when the postman's going to come, and we put people moon with it, we cure diseases, right? So it's obviously on to something, right? Induction works, right? Um, but philosophers as long ago as David Hume, who was in the 1600s, I want to say, maybe I think, um, he uh, he worried about how induction could be justified logically, right? Because there's a bit of a leap, right? It only makes the conclusion probably true, but the conclusion could always turn out false, right? So Hume was a little bothered by that. What good is it, right? If the conclusion could always be false. So Hume argued that induction could never be justified, right? So, observing the sun rising in the east over and over and over and over could never justify the extra leap of saying, well, I guess it will always rise in the east, right? And it's not even clear why repeated observation even makes it probable that it will happen the next time, right? Now you might say, well, in the past, things always seem to happen the way they happened in the past, so I presume that in the future things will continue to happen the way they happened in the past, right? Um, but that's just more induction, right? So you need an extra premise like that states the future tends to resemble the past, and you need some reason to believe that that's always going to be the case, right? And certainly we believe it. Um, why, right? You can't The only justification we have for it is induction, so you can't use it to prove induction, right, is logically sound. And so um, Hume pretty much threw up his hands and said, I don't know how we can ever trust induction or say why it's justified, right? Even if it does seem to always work, right? How can we know it'll keep working tomorrow? So Karl Popper's was bothered by this, right? And he actually ultimately agreed with Hume, right? He said, I don't like induction very much either. It doesn't feel very rigorous to me. Um, but he said that's okay because he came up with an account of science that doesn't even use induction. So Popper said, science doesn't work by induction. Here's how it works. We come up with our hypotheses, right? But we don't come up with our hypotheses by observing a series of events and making it. Coming up with a hypothesis is just inspiration, right? Maybe it comes after you observe some facts, but it's no more logically rigorous than process of coming up, writing a song or writing a poem. You come up with your hypothesis, however that comes about, but that's not logic. That's something else. Then once you have your hypothesis, you test it deductively. So if the hypothesis is falsified, the hypothesis is false. So we haven't learned this rule, this MT that's down there in the lower right corner yet. But what this says is, I think intuitively you'll understand this. Premise one says, if my hypothesis is true, then it makes a certain prediction, right? So that's what we want out of our hypotheses. If Nate is the murderer, then blood should be found, so that's my hypothesis, makes a prediction. If the prediction is false, right? So the squiggle P on line 2, that means not P, right? If the hypothesis, or sorry, if the prediction turns out false, we can say, well, I guess the hypothesis was false, right? That's not H on line 3, and that's using a rule called modus tollens, which we'll learn later in the course, right? So Hopper said this is what science does, right? You come up with a hypothesis, it entails a prediction. Prediction is false, hypothesis is false, and we've ruled out one more bad hypothesis, and we can move on, right? But what this means is, suppose that, again, my hypothesis makes a prediction, line 1, but this time the prediction turns out to be true, right? Um, have I proven my hypothesis to be true? Well, no. Again, as we'll learn later, that's actually a formal fallacy, right? Um, it never makes your hypothesis true. So Popper had to come up with a new word for it. So he called it corroborating. If you have a hypothesis and it's never made a false prediction ever, um, then that's great. That's as good as you can get out of a theory. It's been well corroborated, but we would never say it's true, right? Because we can't prove it's true. So just an example from the history of science. So Newton, Isaac Newton, right? The apple and pretty much the father of like physics. Like for hundreds of years, people thought, well, physics is done. Newton figured it all out. No point in having a physics department. Um, Later, Einstein came along and showed that Newton was pretty good about he got things pretty right about normal sized objects moving close to the Earth, but when you get to moving close to the speed of light, or that's like Newton got it wrong. So I'm still pretty right about a lot of stuff. So Newton studied light, right? So Newton had a hypothesis about light that it was made up of light of different wavelengths, right? It wasn't just a uniform homogeneous thing, right? We all know that now, right? You send it through a prism, and it's like the Pink Floyd cover, and you get all the different colors of light. Right? Nobody knew that before Newton, but he had a hunch that that was what was going on with light, and so he derived a prediction from that hypothesis. Well, look, if light is made up of different wavelengths, then those different wavelengths will each bend at different angles when they pass through a prism. And because the way that the wavelength hits the material of the prism, right, it'll refract at a slightly different angle if it's a different wavelength, right? Um, that's his prediction, right, that he made, and then he does the experiment, right? So he shoots a round beam of light through a prism, comes out, he projects it on a paper, and it comes out oval, right? Because all the different wavelengths were bending at different angles, and so it's spread out, right? So his argument is of this form, right? If D then B, right? So if light is made of different wavelengths, then it will bend, right, at different angles. B, the light bends at different angles. Then again, we said logically that doesn't prove D. Again, you'll learn this a little later in the course, right? But that is not a valid argument right there. It's a well-known fallacy called affirming the consequent, right? So Newton's experiment was successful, but he didn't prove his theory to be true, right? Because there's no deductive way to do that. But interesting, Newton's experiment is what we call a crucial experiment. It tested two hypotheses at once, right? So the experiment also tested the hypothesis light is made up of single wavelength, right? Because that hypothesis also makes a prediction about what would happen, right? If the light is only made of a single wavelength, then a circular beam will stay circular, right? Because it's all going to bend at the same angle, right? Um, so in testing his own hypothesis, he also has tested right, the opposite hypothesis, basically. And that experiment looks like this, right? If S, then not B. If light is all the same wavelength, then it will not bend. B, the light did bend. Therefore, not S. Light is not all the same wavelength. So this is a valid use of modus tollens. Again, a rule that you will come to learn, right? So again, according to Popper, science doesn't need induction, right? It just needs this modus tollens, which is a valid rule of inference. But the downside of that is we can only ever disprove hypotheses. We can't ever prove them, right? We can only corroborate them, and so we'll believe them until a better one comes along, right? That turns out true, and our theory that we thought was good, that was corroborated, we find a prediction that ends up being false, right? And it happens, right? For a long time, we thought that heat was a substance that flows from hot things into cold things. Then finally, we figured out, oh, actually, it's vibration of molecules, right? We learn high, theories that have been around for a long time. Ultimately, always get falsified. We have every reason to believe that our current theories will get falsified eventually, and we'll come up with better ones. And Popper, that's how it goes, right? But that's good. Well, that's enough on induction for now, and I will see you next time.